Darn it. This isn't on a video. Yeah. And then that, what do you think that A1 is?
The slope of the gain.
Yep, exactly. So this A1 right here, this is, go back over here, this right here, this M, that equals A1. And for an amplifier, that is just your gain. So you can see from this equation, when you're describing the response of the circuit, you've got your DC offset, and then you have your gain times how much your input is moving. This is lowercase, so it's how much your input changed. Okay, up to there, good? Okay, so I know I'm repeating. I tend to repeat things that I think are useful. Let's see, should I go farther down here? Oh, I remember what I was going to say. One thing, again, for the people interested in audio, I'm forgetting the exact equation, but the second order harmonic distortion, you may have heard that term, or you may see it if you buy a mic or speaker, whatever it might be. There might be have like total harmonic distortion or second order harmonic distortion. You might have seen that on a box or two. That is actually, I think it's A2 over A1, EI squared or something. It comes directly from this equation. So that's kind of interesting. If you heard third order harmonic distortion, I think that's A3 over A1. So that's where those values come from. And I think there's actually a 2. Is it A2 over 2? Anyways, this is a lie. This is a lie, but it's close. And I actually have it on a slide, and I'll post those slides so you can see what the right equation is. Okay, so if you look at this equation, there's two parts. There's two parts to the description of your circuit. There's the DC part. There's the DC part. So that's your biasing circuitry. And again, you can do this with MOSFETs or BJTs. That'll give you the DC voltage there. And then on top of that, you add the input to it through the AC coupling capacitor that just lets the moving part of the signal through, and then you get your V out. Okay, so this suggests that, well, so there's two parts to the circuit. There's the DC part, and then there's the AC part. And that is, again, really representative of how small signal analysis works. Small signal analysis says, first of all, if you're using this equation and are ignoring all those other terms out here, you're treating this as a line. So if you ignore all those other terms, you're treating this as a line. And if you remember back to circuits 1, there's a particular technique that requires your circuit to be linear, linearly operate linear, the components being linear. You remember that analysis technique where you needed everything to be linear?
Thevenin's analysis? Norton
Thevenin
stuff?
We'll use that later, but that's not what I'm thinking of right now.
Superposition, maybe?
Superposition, exactly. So if all the components in your circuit are linear, then you can use superposition. Okay. And they say, okay, well, this is neat. Okay, we've come up with how to express the behavior of our amplifier in a really simple equation if we're in that little nice linear region of the VTC. Okay, so if everything's aligned, then we can use superposition, and then you say, well, okay, I understand the DC part. So the DC part of it, I can build this circuit. I understand that. I understand this part of the circuit. This is not the math. Our bias. Oh, and also on the homework, I use these terms here, our bias and our load. That's what I was talking about. I took them kind of from the lab manual. So on the homework, that might not be clear. But this part of it, the DC part, that's your first term right here. We've got that taken care of. Small signal analysis is this second part, just the moving part of your circuit. And to do that, you take your DC part and you add it to your AC part, and then you get the total circuit description. Description. That's right? And so we need to figure out the AC part of this. We're talking about superposition here. When you look at your complete circuit, let's circle all the voltage sources here. We've got, here's a voltage source, here's a voltage source, and here's a voltage source. And actually, let me even make this simpler. This whole circuit right here is there to put a voltage on here. The whole job of this left-hand circuit is to put the DC voltage on the base right there to get the current you want to. Okay. So all those are your voltage sources. When you're doing over here, you've already taken care of two of those voltage sources. You've taken care of this one, and you've taken care of this one, and you've taken care of this one, but you haven't taken care of this voltage source yet. So this AC part of the circuit, that is where you take care of just the moving signal. And all of the other sources, remember in superposition, you just keep the signal that you're interested in and you zero all the other sources. Okay, this is where I'm telling my description is maybe losing a few people here. But up to here, any questions? Okay, I don't see any hands up, so I'm going to keep going with this. This model right here, this is the one you've been seeing into the third class now. But this model right here, it takes voltages and it has currents. It's not, what this is about is the change in Vn. But this gives you a voltage and a current. This model right here is not appropriate for finding out when you change a signal, how much, when you change Vn, how much V out moves. So we need to come up with a new model, and you've done most of that work. We need a model that just deals with changes. The DC stuff's already been taken care of by your biasing circuit. You just need to come up with a model for changes. Okay, so there's videos from here on out, there's videos posted, but IC, and remember lowercase means the change in IC. And then IE, ID. Okay, we're going to put something in here that just deals with changes. I know this is fuzzy explanation, so please interrupt with questions. Okay. You found on the math that you did in the last few classes, you found that the change in IC. Okay, let me step back. Sorry, let me step back and just summarize what you did in class so far. We looked at the change in IC with respect to VBE. And for that was IC over VT. You did that derivative in groups. And this is used so often, I gave it a special name. And that's called transconductance. Okay. You also did, we looked at the, we'll talk more about this, but I'm going to just come up with the equations for right now. You said, okay, if I change VC, how much does IC change? And for that one, you got VA over IC. And that's used so much, that has a special name too, RO. Some people call this R out, but I don't like to call it R out because it's not really the R out of anything. So I'll just call it RO in this class. I won't call it R out. And then you also and this was that. We didn't quite get through that math in the first section, but that's what you would have gotten. And this is also used so much, it's called RPi. They gave it another name, so it would be easy to talk about. Okay. So we've got these three. Can you still see that if I make that smaller? Kinda? Yeah. Okay. So this right here tells you how much IC changes when you change VBE. And it's a slope. And so GM is the slope. And then if you multiply it by how much VBE changes, that gives you how much IC changes when VBE changes. Okay. Now another thing we found out, I'm going a little fast here, but we found out that we treat that as the collector and the emitter. The second piece of math we did right here, that we found that when VCE changed, the current through here changed like this was a resistor of size RO. So this branch right here tells you about how much IC changed when VCE changed. And this branch right here tells you how much IC changed when VBE changed. So that's the VCE change, that's the VCE change, and that's the VBE change. Kind of okay so far? Okay, nobody's nodding, but okay, got a thumbs up. Okay, and then we also found out that when you change VBE and saw how much IB changed, it looked like a resistor of size RPi. Okay. And this this model right here has the same 3 terminals as a transistor has. It's got a base, it's got a collector, and it's got an emitter. But it only deals with changes in voltages and changes in current. Okay? Oh, it's so hard to tell if. Go over here and see if there's any. Okay. All right. So let's just use this. We only have 9 minutes left. But let's use this to find the gain, and it's the same example I did in the videos.
Professor, I have a question.
Okay, good.
So you, as you had mentioned before, when using superposition, you need to do it with linear circuits. So how is that possible when you use elements like capacitors and like even a BJT itself? Like they're not linear elements. So how are we able to do superposition? Like
we fudge. So we look at a small enough piece of the graph. We look at a small enough piece of the graph that
okay.
it's like a line. So even your VGS or VBE versus IC, that's clearly not linear. It was like that. That's clearly not linear. But if you take a small enough piece of it, it's kind of close to a line.
Okay.
But it won't. The equation you find down here will give you a different result than up here. So this whole thing doesn't really look like a line to me, but little pieces of it look like a line.
Okay. Thank you.
And more tricks just to make the math easy. So let's look at, go back to that so you can see it. See how we would use this. So this is our amplifier that we're trying to find the gain of. And another bit of notation I mentioned on the videos, but I hadn't here, is if you use a capital first letter and then lowercase subscript, that means it's the DC part of the signal plus the AC part of the signal. So capital and then lowercase. If you just have lowercase, that's just the AC part of the signal. If you just have uppercase, then that's the DC part of the signal. It's a convention in many textbooks, but not all textbooks. This would be B and then lowercase. So if we're looking at this amplifier and we want to find gain, gain is a change over a change. So that's a small signal. That's a small signal value. So we can't use this transistor picture anymore. We need to use this transistor picture. So what you do is you take this circuit just as it is and replace your transistor with this whole thing. So what you've got there is you've got your R, and then you hit the transistor. You replace that with the small signal model. So here's the collector of the regular transistor. Here's the collector of the small signal model. So I connected the resistor to the collector. If I look over here, what's the emitter connected to in the actual circuit?
Ground.
Ground. So what's the emitter have to be connected to here?
Also ground.
Ground. Okay. And then you look at the base. This is the base. What signal is the base connected to here? In. And since we're only caring about the moving parts, it's all lowercase. And then the V out is on the collector. So there's your new picture of your amplifier. It only deals with moving signals. There's a problem here. what did I not do here that I need to do? Think back to superposition.
Eliminate the voltage source.
I heard source, so that's it. So this is the problem. We've already taken care of that in the DC part of the analysis. For the AC part, we need to zero all DC sources other than the one we're interested in, and this is the signal we're interested in. So this actually turns into a ground, and this is called a virtual ground, or some people call it an AC ground. Your actual circuit, it's not ground. But when you're doing this one piece of the superposition problem, you zero all the sources except for the one you're interested in, and you're interested in Vn. So you have to zero this source. Okay. 3 minutes, I think we can do it. Okay. A good step to do after you've zeroed all your DC sources that and you have your circuit drawn out is to see if there's anything you can kind of simplify or prettify. Do you see anything you can maybe get rid of one branch somehow? Okay. Let's look at
The resistors in parallel.
exactly. So R goes from this node. So your R top resistor goes from this node to ground. What about RO? It does the same. It goes from this node to ground. So you can actually redraw this as Can you hear the birds now, or?
I can hear him.
Okay.
Yeah.
Are they as bad as they were?
Professor, I don't think your mic's on because I feel like it doesn't sound different at all.
Oh, really?
I'm not sure, but I was gonna tell you at the end.
Okay, I will test that. Darn it. Okay, so this is our final version right here. And what we're trying to find is, the definition of gain, 2 minutes, equals the change in V out over the change in V in. So that's the definition of gain. So what we do is we take this circuit and you do KVL or KCL and just start coming up with some equations. And from those equations, you massage it so you end up with V out over V in equals some mess. And that some mess is your equation for gain. So let's start doing that. Assume V out's an open circuit. What's an equation for V out? Since we only have 1 minute left, I'll go through it quickly. This current is defined as positive in this direction, going down. But to find V out, you look at the current going into this resistance. So it's actually negative of this current. And this equation right here tells you what that current is. And then that current's going across this resistor. And this is your equation. But what you're trying to get to is V out over V in. So what you do is, after you get your first equation, say, oh, does it have V out in it? Yes, it does. Does it have V in it? Uh-oh, no, it doesn't. So we somehow have to get V in into this equation. Do you see any way to get V in into the equation?
KCL at the node near ground.
Okay, KCL here. Okay, what would that look like? How about it?
Oh, well, Vn over R pi is equal to, or,
That's the current. You're in the exact right place. You're in the exact right place.
okay,
What's this voltage across this resistor?
Vn.
It's Vn, and this is the base, and this is the emitter.
Oh, Vn minus VBE.
It is actually
Vn is VBE.
Vn is VBE,
Oh,
just because the emitter is connected to ground. So you get that. So you can rewrite this as minus Gm times Vn, Ro parallel R. And you say, well, wait a minute. No, what I want is gain, and that's V out over Vn. And if you divide both sides by Vn, you get negative Gm Ro parallel R. And that is the equation for gain for a common emitter amplifier. I kind of sped up at the end there, but any questions? I don't see any question marks going up. Nope, I got a thumbs up.
Do you mind scrolling up on the page a little bit just so I can see what you wrote above?
Okay. Tell me when to stop.
Oh, that's good. Thank you.
Okay.
All good now.
Okay. And there's also a video that does pretty much the same math, so you can check that out
Thank
too.
you.
So can you hear this?
No,
Oh,
I was gonna offer to help during like office hours, set it up and stuff, if that was all right with you.
sure. I just got the computer to recognize the audio port, so that was good. I wonder if there's a switch or something.
It's likely a setting in Zoom.
Okay. I didn't have time to check anything out. Well, it got closer. Kinda. Right. Okay. Questions? Okay.
I have a question. The AC ground is Vin.
The AC ground is anything that used to be a DC voltage
Okay.
becomes an AC ground.
So also Vin.
VN is the signal that we're interested in, so we have to keep that. It's the one source that you're not zeroing. You're doing the superposition problem, but you're not zeroing that one.
Okay, perfect. Thank you.
Good.
Well, thanks, Professor.
All right. Thank you.
Thank you. Have a good weekend.
Sorry, I don't have the mic done. That's so close. Thought I had it.
Professor,
Uh-huh.
I had a question on the homework.
Okay.
This is a really dumb question, but in your video, you showed us like 4 ways to find gain.
Mhm.
All of them are supposed to give you the same answer, right?
They don't. Can you still hear me?
Mm-hmm.
Okay. This is so nice to get this off my ears. Oh my goodness. They don't necessarily. The way you do it in lab, where you look at the peaks, that's generally the least accurate because you get some of this flattening here.
Yeah. So then is like the VPC the most accurate?
The most accurate is actually a kind of simulation that we haven't done yet, and I guess I should have added it to the video. But there's a type of simulation called .tf, and it's actually on the next homework. But it's what it does is I'll try to draw the transfer function. Let's say you have this graph. You want to check the gain for this circuit right here. you find this node. TF finds the gain for you for whatever input you give it. So if you give it an input of 0, it'll give you a gain of 0. If you give it a V in of, 5 volts or whatever, it'll give you a gain of 0. So first you have to find out the V in that's in the middle of the amplification region. So let's say that's like 2.5 volts.
Yeah.
So then you set this to 2.5 volts.
Let me tell you, Bruce.
Your mic's on.
Tom.
Your mic's on.
You put 2.5 volts on there and you run a .tf. And you know how with a dot op, you get currents and voltages, the display comes up in text?
Yeah.
This also comes up in text and it gives you your R in and your R out.
So should we use that method on this week's homework, or do you want us to use one of the 4 from your video?
You can just do peak to peak as long as your input is pretty small.
Yeah.
I used I think it was like 10 millivolts or 1 millivolt as an input. And that gave me my output fit kind of looked like a good sine wave.
Okay. And then I had a second question.
Okay.
For number 3C, where you're asking the questions about like the circuits we plotted, is the reason, I just want to double check like the reasoning that why that circuit is not the best to use. Is it just because like there's a lot of variability?
Let me see. Oh, I know what that was. Okay. Which question was it again?
3C.
Bosco. Okay. Okay. Ask your question again now that I know which question it is. I'm sorry.
So in like the 3C, you ask a lot of the questions about like why this might not be the best circuit to use when setting BBE. Is it just because of the amount of variability when you're like picking resistors, or is there like a secondary reason?
Okay, so I guess everybody here gets a free answer, but how did you improve it, or how did you fix it?
Like better resistors?
That in itself won't fix it, probably. So you had, let's go over the side here. So you had this option. I think this is the circuit you were talking about. Is that it? Something like that?
There wasn't a BJT in the one you gave, but
Oh, okay.
like it was just like the voltage source and then 2 resistors, and then you asked for the V out in 2 places.
Okay, so this one. So the question was, so Bosco had a bad time with the first design, right?
Yeah.
And then the question was, how could you make this voltage more closer to the voltage that you actually want?
Yeah.
And so let's see, let's team. What answers what did you all figure out for this one? It's just I don't know what it might have been, but a better resistor, like smaller tolerance and all that, that won't help this specific problem.
Like we found that the second, like with the bigger resistor,
Okay.
you got the values you wanted.
Okay.
So I just kind of said that was like the fix.
Okay. So make these big, right?
Yeah.
Okay. Or if you left these the same, what would you do to these? I think the question was what could you do to this side? I'll check that, but just for this conversation, what could you do to this side to make it, if you left these the same size, what would you do to R1 and R2 to make it work better?
I'm not sure.
Okay. When you made these bigger, why did that work better? When you made R3 and R4 bigger, why did that make this work better? Why did this voltage get closer to its original value?
Isn't it because the parallel impedance was closer to 100 ohms?
Okay, so you're saying the impedance here, the parallel, if you
like
made
with the 100 ohms and the R3 and R4 together.
Okay. Okay. If I made both of these 100K, would that fix that problem where this voltage changed?
Yes.
Yes. And the question is why? And you're right. Looking at this at 100 ohms in parallel with 200K, where would all the current want to go?
Through the 100 ohms.
Through the 100 ohms. That's the easy path. Okay.
So to make it better, you would make the R1 and R2 smaller?
Yeah.
Or bigger? So that they don't go through?
Well, if you make this bigger, then the current's going to want to split again.
Okay. So rather than making R3 and R4 big, you want to make R1 and R2 small.
That's a solution that works. Okay. What's the cost of making those small, though? Just to rush you a little bit, just because of class.
Oh, sorry.
That's fine. That's fine.
The cost of making those small, but you'd get more current flowing through R3 and R4, right?
Yeah.
That means more power.
More power. Exactly.
Okay.
But the idea of this question is we've talked about gain, and you have a good feeling for what gain is, but the rest of the quarter we're gonna be spending on R in and R out. The birds woke up completely now. The idea of R in and R out, and when you made these big, you made the R in here large. When you change both of these to say 100K, now the RN is large. So what happens to the current going through this direction?
It's gonna want to go not that way.
Exactly. So a big RN just means it doesn't take much current. That's all a big RN means. And it means that if you tested your circuit without connecting it to another circuit and it worked, it will still work.
Okay.
And a low R out means that you can just provide a lot of current and it doesn't mess up your circuit's V out.
Okay. Thank you, Professor.
Is that good?
Thank you.
Right. Bosco is a really dumb bird, but he was my fave. He died. I know it's sad. Okay. All right. Is that good? Then off to lecture. All right. Okay. Not very many people for the second lecture. What do we have? 2, 4, 6, 7. Okay. I did. The headphones work, but the mic doesn't work. And so I forget who said they were going to help.
Oh, yeah, that was me.
Who's talking?
Bruce.
Oh, okay. Is your picture? You just have a picture there, so your face doesn't move.
Yeah, that's my face.
Okay. Are the birds? Is it a real quick fix?
It should be pretty quick. You just have to. I mean, I could take control of your Zoom if you prefer that. I could just do it, but
I'm not supposed to let you.
Oh, yeah, that makes sense. Okay, so
Audio settings.
on the main Zoom, yeah, you want to go to your audio settings.
Okay.
So like the little cog and then audio. And then there should be a speaker and a microphone. You want to select the microphone drop-down tab.
All I have is same as system.
Same system.
Same as system. So let me see, for my system, I have.
Yeah, if you had to set your default for the system.
Yeah, my default for the system is this right now.
Okay. Did you plug does the microphone, like the end of the headphones, does it have two, like a splitter, or is it like?
It actually has 4 sections.
Four plugs?
No, it has the ground, and then it has the stereos, and then it has what I assume is the mic.
Oh, okay, yeah. So left, right channel, mic, ground.
Yeah.
Okay, so if you have a port on your laptop that has both a headphone like a headphone and a microphone together, like you'd plug it in there and it should be able to detect both. But if you don't, then you have to get an adapter.
Okay.
Yeah.
Let's see. Headset, over ear, external speakers, line in. Oh, everything went black. Okay, now it's back. Can you hear me?
Yeah, that sounds, yeah, that's good. Yeah, that's the one.
I'm gonna give up for the day.
No, put your headphones on. Can you hear? Hello?
Apologize.
No. No, it's good. Wait, no, it's good. Put the headphones on.
The story I went through with the first.
Oh my God, it's so much worse.
So I'm gonna use those pictures. So stop me if I start going too fast. The other thing is office hours, because Sunday was picked for the homework due day. I think the headphones work. Okay. So, can you hear me?
Hello?
Yeah, can you hear us?
You hear that?
Yeah.
Yes, but I don't know if can you hear us? Hello?
Yes, I can.
Oh, perfect. Okay.
Cool.
One other thing that I was going to suggest is turning your input sensitivity, like instead of having it automatic, turn it up a bit so the birds aren't always being heard. But
Okay, is that in audio settings too?
Yes, yeah, it should be. There's like a little check mark underneath your volume tab there.
Oh, automatically adjust volume?
Yeah, you want to uncheck that, and then you want to adjust it until we can hear you, but we can't hear the birds.
Okay, how's it going? La 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 la
la la. You unchecked the auto adjust?
Yes.
Okay, I don't actually know where if you can adjust sensitivity. I'm not seeing the tab for that.
Okay. All right. I'll just put them outside. No, I can't do that. Their cages are like one's 7 feet tall and some number of feet wide, and the other
if you hit the advanced tab, there's a tab to suppress persistent background noise. I don't know if that will help with like aggressive settings or.
Okay, suppress aggressive. Okay, does that change anything?
It's not as bad. I think it's a little better.
Yeah, it's definitely a lot better.
Okay. All right.
You're a little muffled, but I think that's it's manageable over the sound of the birds.
Okay, I'll bring the mic closer, see if that does anything.
Yeah, much better.
Okay. Oh, wow. We're finally in business. Thank you so much, Bruce.
Yeah, of course. All right, I'm gonna head out.
Okay.
All right, bye.
Bye-bye.
Oh man, I'm not muted.
All right. Okay. So because of the Sunday due day, office hours ended up, I guess, Friday, Saturday, Sunday, and I okay, not your cup of tea. Okay.
It just seems weird for you.
I don't have a life. I mean, usually I'm the only one without a life, but now everybody doesn't have a life, so yeah. I'm also usually on the computer, most of the day. So if you ever have any questions during the day, just send me an email or, send me an email and I'll, join in. I think that's it. Are you hearing me breathe now? Oh, good. Okay. So I guess this is more effective when we do it from scratch, but let's look at this. This is our topic for the day. And I described, so I have a bunch of videos up that kind of work through the small signal model and how to use it. This is a little bit different approach, and it's not on, actually, let me, nope, stop share, recording this computer. Okay, I give up. I'm not going to deal with anything technical for the rest of the class. Okay, so first thing we looked at here is we had, this is a VTC. So assume this is a VTC for some unknown circuit. And you have a V in axis, x-axis is V in, y-axis is V out. And the transfer function is this line right here. Okay. And I tried to draw a line. It's a little bit curved, but it's supposed to be a line. Okay, and then let's say you have your input described. Say it's a sine wave. So it looks something like that. It's supposed to look like a sine wave. And so this is your input to this circuit. A VTC is kind of like a truth table for analog circuits. It says if you have this V in, then if you have this V in, then this is your V out value. It's a lookup table. So if you have this as your input, it's not the exact same picture as I drew for the other class. Can you still see it if I make it this small? Okay. So what I did was I took this graph right here and I just rotated it as my input. So that's what happened here. I'll rotate this back. And so now what I can do is I can map this input to an output. So for example, at time 0, so here's my time 0 over here, I have, let's say, I have this point right here. I draw that up to the VTC, and where it intersects, that tells me what my V out is. So at time 0, my V out is that point. Is that okay? Okay. And then a little later on, let's say at time 1, get this, I draw a line up, I hit this, that tells me what my V out is. That's my V out at this second point in time. And then if I have a third point in time, That gives you this point. You go up and it comes over here and you draw that dot and it follows the sine wave and gives you your output. Okay, if this is a line, let's say it has a slope of 1, say it has a slope of 1, what's the output look like compared to the input?
The same.
The same. Okay, so for every, if the slope is 1, then however much V in changes, V out will change the same amount. Let's say I'll do the same thing I did over there for the first class. Let's say you made that a gain of 2. How would the output compare to the input?
It would be double.
It'd be double. For any change in V in, you'd get twice the change in V out. So you'd have twice the size of the signal. On the first questionnaire, there were a few people that were interested in audio stuff. Is this a good thing for audio? Have a nice linear relationship?
No.
Mm.
Yes.
Yes, in general. But any of you work with vacuum tubes ever? I know a lot of audiophiles like vacuum tubes. Well, actually, let me bring them up after the next picture. Sorry, but yeah. So this right here, this pretty much reproduces your input to your output, and depending on the slope here, the gain here, it adjusts the amplitude of your signal. So is this picture anything on here fuzzy or good? Okay, so let's go to the actual circuit that we're using in class. And this is very colorful. I'll leave that for now so I don't forget it. But your transfer function for a common emitter amplifier, or as you know it from 307, an RTL inverter, looks something like this. So when the VN gets high enough to start turning on your BJT, it starts slowly and then the current gets faster and faster. So it's probably the steepest somewhere around here. And then when this gets so low that it starts to put this into linear, then it starts flattening out again. Okay, so this is what the VTC for your common emitter amplifier looks like. Okay, so let's do the same thing. But one thing different here is that in this region, you don't get any gain. And we're trying to build an amplifier, so that region doesn't interest us. And same thing over here. Really, you don't get any gain there. So it's really not of interest to us as amplifier builders. So what we want to do is we want to give this one a V in this region that in the amplification region right here between like these two arrows. That's where if you change V in, V out changes a lot. That's a good amplifier. Okay, so this is already drawn out, but let's say at time 0, you come over here and this is the value of Vn. You can draw it up to the graph and that tells you what V out is. And then you can say, oh, at time 0, my V out is that voltage. Is that good for that point? Okay, and then you go to time 2, which is this orange. And so at time 2, Vn is this point. You draw it up, and your your VTC tells you that V out is this value. So you can go over and say at time orange, that's going to be the value of my V out. And then at time yellow, you can go up and say, oh, at time yellow, that's my that's what my V out value is. And you can keep doing points. I have a time green, blue, dark blue, and purple. And you can use the VTC to convert them from the input value to your output value. Up to there, good? Just the same thing we did on the last graph, except the last graph was just a nice line, which humans understand well. This one's a little bit curvier. What do you think this curve up here? It's pretty straight right in the middle here, kind of between these two purple arrows. It's pretty much a straight line right there, but then it curves at the top and bottom. What do you think happens to the top and bottom of this graph? You'd like it to look like this, but amplified. But does it look exactly like this signal over here?
Wouldn't it get like slightly attenuated, kind of flattened off at the top?
Exactly. So what happens here is it wants to do what this pink line does. Is go like it wants to go like that, but up here, for the same change in VN, so for the same change in VN from here to here, you get less gain because this is a flatter part of the graph. So V out doesn't go as high, and you get something like this with. It doesn't necessarily go flat, but it's kind of squished at the top and bottom. Okay. Good there. So because the gain here and here isn't as large as in the center here, this top part of the graph and this bottom part of the graph don't get amplified by the same amount, and you get kind of rounded. And that's why in lab, you are generally measuring gain from the max to the min. This is generally not the most accurate way to measure gain, just because you do often get that rounding at the top and the bottom. Okay. All right, so let's say this is a sine wave. Okay, then this will also be periodic. So this will also be periodic. And do you remember from 228 that any periodic signal can be represented by some sine waves? Yeah, how many sine waves?
Are you saying for this graph in particular, or just in general?
In general.
An infinite number of them.
Infinite number of them. So in general, and for this graph, you end up with, if you want to come up with an equation for what this graph looks like, you have, it's periodic, so it can be represented by the sum of an infinite number of sine waves. I'll make this a little bit prettier. Of varying amplitudes and frequencies. Okay. Okay, and then what you can do with that, and we're not going to do it, and don't worry, you're not responsible for it for this class, is you can take the Taylor expansion of that, and you can then put that Taylor expansion around 0, which is called a Maclaurin series. And when you do that, what you come up with is an equation like this. You have some DC value plus some coefficient times your Vn plus a second coefficient times your Vn squared plus a third coefficient times your Vn cubed, dot, 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 all the way down to some coefficient infinity to your input voltage to the infinite power. Okay, so a couple questions here. if this transfer characteristic was exactly a line right here, if this transfer characteristic was exactly a line right here, what do you think A2, A3, all the way up to A infinity would be? All the coefficients.
They'd all be the same.
They'd all be the same, and they'd all be for a line.
The slope.
A1 is the slope, actually. Those all are related to the slope. But if you're doing a line, do you see something that looks like the equation of a line? It's just these first two terms of the series. Turns out if you have something that's a line, all of these coefficients, A2 down to A infinity, are 0. And that makes humans happy because humans don't like V to the 25th power and V to the 7,922nd power. They don't like to do math with those. Humans don't like that. So it's nice that if you have a line, everything but these first two terms go away. A second, I think my doggy needs to go out. I'm sorry. Sorry, he's been walking to the door for the last half hour. I thought I'd better let him pee. Yeah, so all of these go to 0. But is this line, is this a line right here? Is this a perfect line from the top black arrow down to the bottom black arrow? No.
No.
Yeah, so those coefficients for this particular transfer characteristic are not all 0. But this middle part right here, that's pretty linear. So if you could come up with this series, these would be very small enough to ignore. And I say small enough to ignore, but if you're calculating the orbit of a spaceship and people are going to die if it's a little bit off, then you want to possibly take those coefficients into account. But if you're doing the Energizer Bunny and it just needs to clap, kind of every few seconds or something, and nobody's going to die, then say, hey, well, this whole thing, it's close enough to align. It's close enough to align. Whoops, wrong picture. This is close enough to align. We'll just consider this whole thing a line. Okay. So that's a little bit application specific, how careful you are in approximating something as a line. But in this class, we're pretty much going to say, hey, good enough. Looks like a line is a line, which means all of these terms go away. And you're left with this. Okay. And this is actually kind of interesting. Let me go down and see if I have a picture. Oh, that was another explanation. So we have this equation right here. A naught, that's just a constant. And if you look at that in terms of the circuits that you've been building, that is actually your biasing circuitry. It sets a voltage on the input to your amplifier to induce a current. This voltage right here, that's your A naught. So if you're taking this equation and trying to apply it or match it up with your common emitter amplifier, this first coefficient is your DC offset. It's your DC value going into your amplifier, and it's coming from your biasing circuitry. Okay, and then the AC part of it is when this moves, how much does V out move? So V in it's lowercase, so that means it's how much V in moves. And if you remember, the way you put a moving signal onto this is through this AC coupling capacitor or DC blocking capacitor. That's how you'd let just the moving part of the signal of your input signal to be kind of superimposed on this DC or added to, just like it says here. It's added to that DC voltage. Okay. So the second part is this AC part. And it turns out here's your DC part. So that's the circuit for your DC part. And there's two pieces to completely, for the total description of your circuit, there's two pieces to it. There's this DC part, which is the first term, and then there's the AC part, which is the second term. And so if you give it a moving signal of VI, what do you think this A1 is? You already said it a minute ago, but
Would that be the gain?
exactly. Okay, so this equation says, okay, you've got your DC, here's your DC stuff, plus your AC stuff. So you have your gain times your input voltage. And that you add the two, and then you get your total circuit description. Up to there, good? Okay, so let's see. It's a good thing we weren't redrawing it because we're about at the same place as the other class, even with the talking at the beginning of class. So, okay, so it turns out that a transistor, this transistor that you've been working with for the last 2 quarters, that doesn't describe gain. Remember, gain is the change in something over the change in something else, change in V out over the change in V in. Okay, and a transistor runs on voltages and currents, not changes in voltages and changes in current. So this is not good anymore. Okay, and last time we talked a little bit about it, but we need a model for the transistor that just tells you when I move this node this much, how much does this other node move? And were all of you here? Wait, today's Friday, right? Okay. Were all of you here Wednesday? Yes, 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 yes. Okay. So I think we put this together, did we?
Yes.
Okay. So we've got our 3 values, our 3 parameters, small signal parameters that describe how transistor changes its current. And we put that together into this model. And it turns out, remember, we've got this DC part plus the AC part equals the total circuit description. This AC part is described by this model right here. Did you, since you got to see it a couple of days ago, do you have any questions on it, how we got there, or? Okay, so then let's keep going. And one note on notation while I'm here. If I have a capital first letter and then a lowercase subscript, that is the DC plus the AC. So that's the complete behavior of the circuit. If I just have lowercase, then that's just the delta. So that's just the AC part. And if it's all uppercase, then that's DC. And that's a notation that a lot of textbooks use. I'll try to use it the rest of the quarter. I get lazy sometimes, or I get forgetful sometimes, but I'll try to use that notation. Okay, so let's work out a gain of common emitter amplifier here. So this says it's capital V and lowercase in. So this is the DC bias from the biasing circuitry plus that input signal. So this says both in. And V out also capital V lowercase OUT. So that has the DC output, basically the offset, and then plus the moving signal. Okay, so we want to find gain. We know gain is delta V out over delta V in. From our notation, we know that's V out over V in. Okay, and we said when we're trying to find small signal values, gain is a delta over delta, so gain is a small signal value. We can't use this model anymore. It's hard to work with. So what we do is we replace this. Did we get to this part at all? Where we replace the transistor with the model? I don't think we did, right? Okay, so that model doesn't work well. So we know there's a transistor in this circuit, so I'm just drawing the transistor now. So I just drew the transistor, but as a small signal, the small signal model of the transistor. Okay, so that's this right here. Okay, and notice this, just like the actual transistor, this has 3 terminals. So you're actually just exactly replacing the transistor with this other model. And everything has to be connected to the same as this circuit. So in this circuit, what's the emitter connected to?
Ground.
Ground. So connect that to ground. And then what's the base connected to?
VN.
VN. And since this is a small signal model, it only cares about the changes. So I make that a lowercase. What about, where's the resistor connected?
C.
Okay, so the resistor is connected to C. Let me do. Okay, and what about V out?
Also C.
Also C. That's not very good. And now we've redrawn our circuit, but now to look at the moving part, the moving signals. The other big part of this was superposition. And when we're using this model, we only care about the moving signals. So the deltas. So any other voltage sources, you need to ground. So are there any voltage sources in here that aren't related to moving signals?
VCC.
VCC. So we take VCC and we actually ground that one too. Okay, so we've done all the preliminary work now. A good step to do after you've replaced this transistor with a small signal model, a good next step to do is to see if there's anything you can, I call it prettification, and it's actually a word, I looked it up. But if you can get rid of a branch somehow, it's good, it'll mean less work for you. So do you see any branches here that we can maybe combine or?
RO and R are in parallel.
Exactly. So R goes from this node to ground, and RO also goes from that same node to ground. So they are actually in parallel. So let me redraw that. And this already looks like a super weird circuit. You've got V out kind of floating up here at the top. No supply. Supplies all get grounded because they are taken care of in the DC part of the problem. And now we're in the AC part of the problem. And yeah, so this is our circuit. So again, just to remind you, we're looking for gain, which is V out over V in. And the way we find this equation is we just start doing KVL and KCL. We try to come up with the equations. Lots of times when you look at these circuits, after you replace the transistors with a small signal model, it's really hard to see where you should start. So just start making equations. So since I know where to go actually, let's come up with an equation for V out. Let's see. So hint number one, this current source, it's defined as positive in this direction. Now that I've messed it up. And assume no current goes out V out. So no, what's the current going in this direction?
Negative GMVB.
Yes. Okay, so this is a current source and the amount of current going through it is just exactly GM times VBE. And you've defined it, this direction is positive, so the current going in this direction is negative GM VBE. And none of it's going out V out, so what is V out?
Negative GM times VBE times R not in parallel with R.
Exactly. Okay, so we've got an equation, right? So for all of these derivations, or when you use this small signal model to find gain, or you're also going to be finding R out and R in. Remember, for an ideal op amp, R in equals infinity, R out equals 0. We're going to use the same model to calculate R in and R out, as well as gain. When you do that, good thing to do is go back to your original equation, and you want V out over V in. So you need V out and V in your equation. So let's see, V out, that's in the equation. Okay, good. GM, that's not a voltage or a current, so we get to ignore that. VBE, that's not in that equation. So we need to get rid of VBE somehow. Can you see anything we can do with VBE? We have V out in the equation. What's the other voltage we need to have somewhere in the equation?
VN.
Exactly. So that's what we're missing.
Can we do a KCL on that bottom node right above ground? And
think simpler. You can, and it'll get you the answer. But if you remember, this node right here is the base. This node is the collector. This node is the emitter. So what's this voltage right here?
VBE.
VBE. So VBE equals
VN.
exactly. So you can directly replace that. V out equals negative GM VBE RO parallel R. Oh, the whole reason for doing this was to replace VBE. So we're not do that. V in. Okay, so good. Now the only voltages or currents we see in this equation are ones we find in this equation. So that's good. But what we're looking for is for V out over V in. So we got to take this just one more step to get V out over V in.
Just divide each side by V.
Perfect. And now you have the equation for gain for a common emitter amplifier. And if you notice, like there's GM right here. If you say, well, wait a minute, I don't know the value for GM, you have to go back to these equations right here. You know GM equals IC over VT. And you biased your circuit to have a certain current through it. So that's your IC, and VT is your 26.9 millivolts or whatever it is. So if you could have put this right into the small signal model, but now you have fractions going on in there and other stuff. It's often much simpler to solve using GM and RO and RPi. And then when you want to find a value, just go replace those with the IC over VT and the VA over IC. This is just to make it a little bit prettier, but it's not really necessary. But most people solve to here and then replace it with the IC over VT or whatever. Okay. Questions on that?
So when we're finding the gain in homework question 1, will we disconnect our the mirror side and just find the gain there? Okay.
Yes. Yeah, you have to because of the AC coupling capacitor.
Yeah.
Well, if you do a DC sweep, there's other options. And there's actually one that I didn't put in the video that somebody asked about. So is it okay if I scroll away from this picture? Okay, I'll post this later. Where did I put that? Oh, there it is. Okay. So there's another kind of simulation. It's called .tf, the transfer function simulation. And if you have, you know how when you do a dot op or a DC bias point simulation, it comes up with text? This also comes up with a text window like that, and it gives you gain, Rn, and R out for your circuit. But it does it for whatever input voltage you put on your amplifier. So if I put 0 volts here, it would look here and say, oh, your gain's 0. It wouldn't give you a good result. So when you use .tf, you generally have to do like a DC sweep or something. Find a voltage where you're in the amplification region, then set the gate, to that voltage. And then if you just do a .tf, it's just, you can, it's in the simulation window, you can select transfer function, or actually, do I have it up? Oh, I don't. I had to kill my computer earlier today. Lost a bunch of stuff. Oh, actually, let's do this. Oh, what was I going to do? Oh, yeah, I remember what I was going to do. So if you go to simulate, there's the DC transfer. They call it DC transfer. So if you go to DC transfer, and there's some special syntax for that. You do V, and then whatever your V out node is, and then your source. I think you give it the voltage source name. I'm supposed to say V out. So you have to say, I want you to watch voltage on the output, and then you give it the source as the input. When you put V in parentheses, it tells the simulator, I want you to find the voltage at this node, not the current.
And so you're saying when you're at this point, you've already found a voltage that you want to look at. So that V1 is that voltage.
Yeah, you would take, all the answers are sitting here, but you put a DC source on the, you take your common emitter amplifier, you take your common emitter amplifier and put a source on the base. In our case, in our example, it was 2.5 volts. So you'd put a 2.5 volt source on here. And then that would be the input source. That would be the input source. That's actually on next week's homework, but if you wanted to use that, that's fine. If you want to use peak to peak, that's fine. Just know that the peak to peak is probably not the most accurate way to find the gain.
Okay.
So anything else?
I don't want to keep you, but
I'm fine.
will there be any talk about the tube amp that you were kind of mentioning?
Which one?
Like a tube amp or a vacuum tube?
Oh, we don't talk much about vacuum tubes. Oh, that's right. Okay, back to that. So totally forgot about that. So the common emitter has a transfer function, something like this. A vacuum tube is basically an amplifier. It's like transistor. So it also has a transfer function. It's shaped a little bit differently, and therefore, those coefficients, those later coefficients aren't zero. And a lot of audiophiles think that gives you a nicer sound. But that reminds me, I forgot about just one last thing. You can go if you'd like. But if I think speakers have this spec. I'm not much of a music person, but I think speakers have these specs. Maybe these headphones have these specs. But have you heard of like second order harmonic distortion and total harmonic distortion? I have the equation in the slides and I can't remember it off the top of my head. But for example, the second order harmonic distortion, it is actually, if you want to find a value of it, it's a relationship between all of these coefficients. It's how big these later coefficients are. So a second order harmonic distortion, I think it compares the second coefficient to something. I couldn't remember, so I wrote A1. But like third order would be the third order coefficient. Total harmonic distortion is the sum of various coefficients. And I can find notes on that if somebody's interested. Yeah, that's where those numbers come from.
Okay, I might email you about that, notes on that, because
Okay.
I find that very interesting.
Okay. Yeah, I'd have to find my reader. I had a great instructor, but he was just so smart. I'm not sure what I learned in the class because it was just always over my head. But I do have his notes, and we talked about that for like 4 weeks.
Okay, cool. Thank you very much,
Right.
Professor.
Absolutely. Right. Yeah, and again, office. Oh God, these things really squish my head. Office hours, evenings, Friday, Saturday, Sunday. if you don't have any place to be. Actually, there's a dance tonight, a Zoom dance that I was going to go to. So you may have to watch me dance while during office hours, but yeah. It's pretty
Have a
fun.
good weekend.
Yeah, you too. Right. Night.
Will we ever get to see the birds?
Oh, I can point out my house is a disaster area right now. I
Oh,
have
no worries.
I have mice, so I have all the furniture upended. But yeah, let's see if I can rotate this. Let's stop sharing. Then get rid of background. How do you say none?
I think you have to like choose a background, and then one of them is none.
Okay. Oh, none. Ah, there it is. Okay. Then let's see if I can pick this up. I've got so many cables hooked up to this thing. Oh, there's my very expensive treadmill that I invested in.
Mm-hmm.
Oh, we're almost there. Oh, I can't rotate it much more.
Oh. Hi, birds.
Hi, birds. You can't really see it, but
That's
there's
okay.
a long cage all the way along one wall.
It's the thought. Oh, I see them moving too. Oh, wow. Yeah. Those are big birds. Anyhow, thank you very much for that.
Everything's falling over. All right. Then I'll be available tonight. I have to go on a doggy walk now, but then I'll be available tonight if you have more.
Okay. Thank you.
All right. Talk to you later.